trying to get him. He was like, he's just drowning under this load. I'm like, you're not recording your class? Like, he's coming up with an alternate assignment. It's like, dude, you're killing yourself. Just record it. It'll alleviate so much pain and suffering on your end. Y'all gotta poke your head in there and say hi to him. I poked my head in there and he's like, he just looks like somebody's knocked him around. Anyway. Elmer's?
Yeah.
No, he's still in the same room.
Everybody during
Which is the English pod, right?
No, that math part?
Oh yeah, I forgot we're not in the math pods, the history pod.
Yeah. All right, so couple things that were new. I think they were new. Compounding interest. Right? And the big thing to know about this is the P stands for what? The principal, which is the starting amount of money you have. A is the ending amount, right? R is the rate, and when you plug it in, this is a little bit different. At the end of the year, we're going to do a finance course in here, and I'm going to show you about time value of money. In your calculator, you type the rate in. Like if it's 6%, you would just type in 6. But here it's important to move the decimal and write it as move it 2 places to the left. So if it's 6%, put up 0.06. The ends are the same variable. That stands for what? The number of times you compound each year. So if it's quarterly, it's 4. If it's weekly, it's 52, roughly. Monthly, 12. And monthly is probably more reasonable. Most people would compound monthly, even though maybe in the olden days it might be quarterly. Sometimes it's an average daily percent, like a bank will look at your account and they'll say how much money do they have at the end of the day over the 32 days. They average that, and that's what they call your amount that they give you interest on, which doesn't really matter because interest rates are like 0.0001. So you get really nothing. You're just letting them borrow your money for free. And then the T is what? Time in years. So if you're compounding quarterly, that 4 gets multiplied by the number of years, and that's how many total times they're compounding over that yearly period. And what you're going to have to realize is that I'm going to maybe give you everything but T. And how would you solve for everything but a T? How do you solve when you're looking for an exponent variable? Careful, let's just say I had something like, I'll give you numbers you can probably do in your head. What if I had something like, I don't know, right? And you say, well, I can divide by 2, that part I can do, and I can actually add that together. But how would I solve for the T? If a variable is an exponent, you'd what? We're going to talk more about this today. Log it. The only way to solve for a T is to log both sides to remove this and let the 4t kind of fall down. Remember this? So I would log, but what kind of log would I have to use to get rid of that? It's been a while. A 1.03. So I'm going to log that 5, which who knows what that number is. And then I'm going to log that, which is what we're going to talk about today. And then what does this rule tell me? That cancels. So if my variable's up here, I'm going to have to log both sides at some point. Now, yeah, I can divide that out, and I can add this together. But at some point, I would have to do that. And again, I don't know what that value is. Who knows? We'll figure it out. But my guess is, I don't know. It's not small. And then I would divide by 4. Are you with me? And then sometimes you'd have a variable here. What would you do if the R was still left and say you ended up with 48 right here? How do you get the R by itself? You're going to talk louder. I can't hear. How do you get the R by itself? Close. It's not a square root because you're not getting rid of a 2. It's a 48th root. Do y'all know you have a 48th root button on your calculator? I mean, you have an nth root button.
Yeah.
Not a 48. But if you go to your calculator, right where the little caret key is, you know how you do an exponent? Right above that, you'll see n root x. So you can literally go in there and do the 48 root of 5. Now that root and that root cancels. Now because they're even roots, technically you get what? Anytime you have an even root, I'll remind you.
Absolute value.
That's right. Anytime you have an even root, you get absolute value, and absolute value gives you plus or minus. Right? So you don't have to write that absolute value, but because it's an even root, technically you have plus or minus here. So it's ugly value, but one of these is not going to make sense in the end. Okay? And it's going to be the negative one. So you probably could just ignore the negative. But anyway, then you could subtract. Sorry, that's not an n, that's a 4. But you see how that cleans it up to the point where I can now subtract 1 and multiply by 4? Right? And then sometimes you're going to have, you will not have the n's missing. That's too complex for you to do at this point. You could do it, but you would have to do it with a calculator. You would have to graph it. And you'd have to solve that way. I won't give you a question like that. But it is possible for you to also have p missing. What would you do in a situation like this? Yeah, you can
add it and just solve that.
That's right. Yeah, you can go ahead and simplify all that, can you? You can add that and get this, and you can raise that to the 48th and get some other big number. And then at some point, what do you do to solve for p? Just divide by that number. So that's the kind of math, and I doubt I might have done an example or two. I forget because the video was a while ago when I did it. I'm trying to stay at least a week ahead. But make sure you can solve for any variable. And of course, if you're solving for a, you can just type this straight in your calculator. All right? And then the only other question, and I don't know that I did any problems on this, was the PERT. And this is a form people use for investing, but the more common form is this. And we use this in calculus all the time, because this equation is an exponential growth equation, or an exponential decay, depending on what the exponent is. And this is very, 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 very common for AP Cal, except in AP Cal we give you this, what we call a differential equation, and you have to solve the differential equation and turn it into an actual solution. So this would be the solution to the differential equation. But the math that you will learn in calculus to get from the differential equation to this, you can skip if you recognize it's exponential. So I train all my kids to go, wait, that's exponential growth. Let me just start with this formula, and then I don't have to go through the calculus, save myself 3 minutes, get more done on my AP test. But anyway, you see how this is essentially the same thing? You have this rate. Well, this is the rate of growth or decay. Then you would find that K value. This is the number of years or time. It might not be years, it may be days, whatever. Final amount, initial amount. So it's important that you know how to use both these, but you'll notice there's no compounding, right? Because this is continuous growth. So what does that mean? How many times do you compound a year if you're continuously compounding? How many times is that? Say it, you're thinking it. An infinite amount, right? Now watch the math on this. First, you need to know this. E, even though you don't know really what a limit is the limit of 1 plus 1 over n to the n as n goes to infinity. And you look at it, what the heck does that mean? Well, that means as n gets bigger and bigger here, like not 100, not 1,000, not a million, not a billion, not a trillion, not a quadrillion, not a quintillion, whatever. As n goes to infinity, huge, this value starts becoming closer and closer to 2.7182811, and then it starts changing. There's no pattern. It's like an E. It's like a pi. It's irrational. We just say it's about 2.7. But if you hit E to the first on your calculator, it'll spit that out. And the bigger n gets, the more it looks like this. Now watch this math, and I think I put this on your sheet. But what if I made this clever little substitution? What if I said, let n be Rm? And they may go, why in the heck would I do that? Well, I'm just going to do a substitution, which we've done in the past, right, to make factoring easier or whatever. And as long as, if R is a constant, that's the rate. If R is not changing, what happens is n gets bigger. What would have to happen if this was true?
N gets smaller.
No, if R is constant, like say R was a 3, and N is, I'll make it easy, 6 and 2 would be true, right? If N gets bigger, then to make this true, what has to happen to the M? It would have to get bigger also. Maybe not at the same rate, but it would also have to get bigger. So if I make a substitution, watch the magic here. If I replace the N with Rm, it becomes this, right? And if the R's cancel, it becomes this, right? Because the order doesn't really matter. And is this any different than me doing that? No, because power to a power, I'd still multiply, right? And does 1 plus 1 over m to the m look familiar? So if I were to tell you, hey, the number of compounding periods is becoming so common that it's approaching infinity, and as n approaches infinity and the r is constant, what would have to happen to the m? It would also have to approach infinity. So if the m is approaching infinity, then what is happening to this expression right here? It's becoming what? E. And that's why all of this becomes an e to the RT. And that's where that formula comes from. I'm not going to make you prove it, but if you ever go take a math, if you ever get a math degree or something similar, you might take a proof course and you would have to walk through things like this. But this is why this formula works. It's not magic. I used to wonder, where the heck did the E come from? Because my teachers never proved anything. But it's kind of nice to know, I think. And I think this is even in your notes. But make sure you understand how to use these things. And then also when it comes to half-life and things like that, I want to show you a little trick. A lot of times you'll be given stuff like this, like, hey, somebody gave me 1,000 grams of some radium isotope, I don't know, right? And I want to know, or maybe I say something like, hey, the half-life is, let's just say 200 years. Well, when you think of, and I know it's exponential growth, because you know half-life, right? If you think about half-life, that means, okay, if I have this much amount now, at 200 years, I'm going to have half that amount. And in another 200 years, I'm going to have half that amount. And in another 200 years, I'm going to have half that amount. But what am I looking at here? I'm looking at an exponential growth, but just going down instead of going up. So if you know it's exponential growth, which you should if I ever say half-life or double life or fourth life, all right? If you know that, then you can say, well, looking at this formula, if I have 200 now, and I know that it takes I have 1,000 now, and I know that it takes 200 years for this to go in half, couldn't I say it takes 200 years for this to go to half, which is 500? But I want to show you something that happens every time. If I'm solving for k, which is my growth constant, it shows how I'm growing on this curve. Look what happens on half-life every time. What would you do first to solve for k? Divide by 1,000? Oh, half-life. Oh my goodness. What would you do next to solve for k? And remember, e is not a variable. We don't want to solve for e. I know what e is. It's about 2.7. Natural log it? Cancel, cancel. And then lastly, divide by 200. So when I do this, my k value, and I teach my calculus kids this too, my k value is that, or whatever my calculator spits out. Well, couldn't I just find the k value real quickly if I wanted to? Just remembering that if I'm ever dealing with half-life, it's ln of a half over how many years it takes to become a half. And then I save myself all this trouble. So if I'm given a problem like this on a calculus test, which is where you guys are heading, I'm assuming, right? You could go, oh, half-life. So I'm going to have to find this k value to be able to work with this problem. So let me just say, hey, the k value is the natural log of a half over 200 years. And now I've got the k value. And then I can just go in and I am ready to go in this equation because y is the final amount, c is the initial amount, k I now know, and you can type it in your calculator if you had a calculator, times number of years. And I have my formula ready to go, and I'm ready to jump into action. So now if they say, hey, how much would you have left after 50 years? Plug a 50 in. Bam. If they said, hey, how long will it take for this to go to 10 grams? How long? Put a 10 in there, solve for t. And you can just do the algebra now. One thing I do want to caution you about is if you ever type something in your calculator to get a decimal and you round it, it's totally fine to round on your paper. But you must use that value over and over again. Do y'all know that? So do y'all know how to go in your calculator and move up and grab a value? I know how you probably know how to do second answer. But do you know that you can kind of scroll up? Do y'all know this? Hold on. Okay, give it a second. So I just want to show you that your calculator is really great. So if I need to reuse a value, maybe that I found 5 calculations ago, I can just set up the problem in my line and then go up there and hit that value and hit enter, and it pulls it down in. So for instance, gosh, I don't know. I'll just show you something. Assuming this was gonna, there we go. Okay, so check this out. Okay, so say I'm on my calculate page and I want to take 1,000 and I want to divide it by that, can't see. Say I want to take 1,000, but I want to divide it by that number. Or maybe some number that's way up the screen that's already rolled off the screen. I can just hit divided by, and then I just go up and highlight it and hit enter. Bam, it pulls it back in. And it'll pull the exact value in. This is a rounded value because I have it set up at 5 decimals. It'll pull that exact value in, and now when I hit equal, I'll have my result. And that's really great because now I don't have to just write the number down and use that rounded value. Even though it's rounded to 5 decimal places, this will keep me exact. And I want to be really, really exact when I'm doing calculations like this. Right? Because think about this. What if you put money in the bank? Right? And you were doing this and you did a little rounding. It's like, oh, well, it only affected your account by a couple of bucks. Big deal, right? Well, if you have 100,000 people in your bank and it only affects them by a couple of bucks, that's hundreds of thousands of dollars. That's fraud. And at the very minimum, it's a crime. Maybe you're not. Maybe it's a misdemeanor. Maybe you could claim stupid. But ultimately, you really want to be exact in things like this. And I think, did I ever tell you that story about the guy who was they were building the bridge, not the bridge, it was actually a interstate, but it was elevated interstate in Phoenix. I can tell you this, it's a true story. They were connecting I-10. I-10 goes from like Tallahassee, Florida, all the way to LA. And it stops just shy of LA when you're going into town. And if you just keep on the main road, you end up at the Santa Monica Pier. Anyway, it used to be broken in Phoenix back in the 80s. Not broken like broken down, but they'd never connected it. So if you got off the interstate, you had to drive through Phoenix. So what would normally be like a 35, 40-minute drive would be a 2-hour drive through traffic, hitting every single light in Phoenix. So they built this road. Well, they were building it from both ends to connect it. And they got close enough and they realized, we're not going to connect. We didn't do the calculations right. And they missed it. So they had to rip down sections and redo them, and it boiled down to a rounding error. It was hundreds of millions of dollars. They had to rip down and redo. And of course, that doesn't go over well with taxpayer dollars. So anyway, we want to be really careful with our rounding when we're doing this stuff.
Wait, so you said that we can round out our paper, but we still use the big version of it?
Correct.
Okay.
The only thing that you really want rounded permanently is your final answer.
Okay.
But you can round as you go, just in the interest of time. A lot of times you'll see me, even though it's not really great math, like I'll write down like 2.374 dot 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 x equals 5.276. I'll do that in maybe a key or something so you'll kind of see what I'm doing. But ultimately, you're welcome to just round it, as long as when you do your real calculation, these are not rounded. These are exact. And then at the very end, round that. Are y'all with me? Because it really can get off. And sometimes getting off makes a big difference. You know, like if you're thinking about shooting a target, you know, with an arrow or something, you get off a very small part of a degree. Over the course of 100 yards, you might be missing by a foot or two, right? So those really small measurements over the long term start adding up. And when you start doing that with exponential growth, with money or things like that, you start missing calculations and getting bad predictions and that kind of stuff. So anyway, so that's kind of a review of what we did. Today I think you'll think is a little easier because we're just going back over some log rules. Okay, so some of the log rules I want to talk about, and if you read back through your book, there's all kinds of little formulas, and even in your book, there's all kinds of formulas and stuff. But I want to make sure you understand a couple things. All right, so if I start you out with an exponential function, so this is what we were talking about yesterday, exponential functions. All right, this function is related to a log function by being an inverse. And in fact, I'll make it kind of easy. I'll take that a and make it a 5. What did we do to find an inverse? Do you remember? To determine an inverse, what did we do? We switched the x and the y, and then what did we do? We resolved. And the resolving is just to make it look pretty. Technically, that's the inverse. But if I want to resolve for y, what would I have to do to get y by itself? I'd have to log it, right? And some people used to just always log with base e, natural logs, and then do a little division or whatever. But we've been dividing by a log base 5. Logging it with a base 5 when I'm trying to get rid of that, and I think that's a little better. And watch, it cancels, and I end up with y equals log base 5 of x. Now look at these. These are inverses of each other. And what's the property of inverses that we've learned? What do we know about inverses?
They
Are
symmetrical over the one over x, which is y equals x.
great. They are symmetrical or reflections. I really like symmetrical over the y equals x-axis. So if you check out the exponential function, it kind of looks like this. If you were plotting points. And if you check out this log curve, it kind of looks like this. And even though that's not a perfect reflection, you can see that it kind of is, right? Now, to be able to understand all this, you can learn all this stuff, and hopefully this is all ringing a bell to you. If you're wondering where I got these 2 points from, well, there's some log rules that help you simplify without having to overthink. Okay? Log rules that help you think in terms of a log as opposed to think about everything like this. And a couple of them are this. If you ever have a logarithm, and it doesn't really matter what the base is, okay? If you're logging right here, first 2 things you have to consider are this a and this b. Are you even allowed to have every value on the planet there or there? And the answer is no. For the b, what has to happen? It has to be what? For the top value, oh, I may have these in a different order in your notes. In your notes it might be BA. But whatever they are, I'll tell you, I'll make them CM just to be different. For that top number there, what does it have to be? Think about it. What numbers am I allowed to plug in a log curve? Only positive numbers, right? So the value here has to be positive. But the base value, it not only has to be positive, right, the C value, but it also can't be what? can't be 1. Now, don't confuse positive but not 1 with greater than 1, because it actually could be all those fractions in between. Okay? And if you're wondering about this, that has to do with the change of base rule. If I change this to log m divided by log c, if it was equal 1, you'd have a log of 1 on the bottom. And we know that the log of 1, which is another thing, no matter what this is here, is always equal to what? 0. And that's where this first point comes in. It doesn't matter what kind of log curve. If I'm logging a 1, I'm going to get a 0. So you're always going to get that point right there, unless there's a shift or something on the graph. And then also, we learned some log rules that said your book will always give you this one. If you ever have a log and you have a power there, if this can be written, if this number that you're logging can be rewritten so that these two things have the same base, what happens? And this is what we do when we log both sides of something. We've done that already today, right? You pick the base so that it matches that, and then you cancel them out. So this would just cancel, leaving me an m. And that, your book gives you that, but what I've noticed is that even if there's a power there and it's different, you can still apply this rule, but you're not left with m, you're left with what? M over n. Now it's important to see, and this is going to get really tricky in some of the logs we do, what does that imply about this? What would this give me? 1 over n? Now I have a question. If this gives me 1 over n, okay, follow with me. What would this give me? Same thing, because what's log base x of x? 1, and 1 times 1 over n is 1 over n. And aren't you allowed to take numbers in the front and swing them up right here? Aren't you? And if I did that, what would this be equal to? Still 1 over n? So doesn't that imply that this n on the bottom is the same thing as taking that n, which is the power on the bottom, and making it a 1 over n power on the top? Or if you want, take that n right here on the bottom, make it a 1 over n out in the front. Are y'all seeing that? So this is going to be a really big, and they don't teach that in most pre-cal books, but it's a math team topic all day long, because they'll ask you to do stuff like this. What's log base 4 of a plus log base 8 of b? And you're like, well, I can't add those because my bases don't match. And in a normal pre-cal, they'd go, yes, you're right. Good way to catch that. But we can do better, because both of these can be written as what? Base 2. And if I change that to base 2, and that to base 2, what is this 2 the same as? So that 2 on the bottom could be rewritten as a 1/2 up here. And this 3 on the bottom could be written as a 1/3 up here. And now what do I have? I have like bases. And as you remember from last year, I'm guessing you can't add unless you have like bases, but now I can. And to add these two logs, what would you do? Do you remember that? To add two logarithms, somebody remembers, multiply these two numbers. So you combine it into one log with that base by multiplying the a to the 1/2 times the b to the 1/3. You see it? Now, if you're really creative, you can do some other things too. Like, let me ask you a question. Hold on to that thought. What if I multiplied the front here by 3 over 3? Am I allowed to do that? Yeah, because 3 over 3 is 1. What if I multiplied the front here by 2 over 2? Am I allowed to do that? And couldn't I take this 3, because it's out front, and swing it up to that a? Isn't that the same thing? Because if the 3 was right there, I could swing it out to the front, right? It would be 3, and that's a 3 over something. And then couldn't I take that 3 and swing it to the 4? Does that make sense? So doesn't that kind of suggest that we could just cube both of those, or square both of those, or raise them both to the 5th, or do any power I want, right? As long as it's the same power. Which is odd because we can't do that to a fraction, but we can do it to a logarithm because of our log rules. What does that imply about the 2 over 2 then? Top 2 goes there, bottom 2 goes there. Well, now what do I have? Log of 64 as my base, a cubed, log of 64, b squared, which would be what? Log base 64 of a cubed b squared. Now it looks like these two are totally different, don't they? Well, there's a lot of logs that look different that have the same value. But if you really look at this, what would you do if I took this, based on this new rule we just have, and I raised that to the 6th and that to the 6th? What do you end up with? 64, a to the half to the 6th, a cubed, b to the 3rd to the 6th, b squared. So how do I like it? I don't care. You can leave it as this first one we did, or that second one. I gotta be honest, sometimes it's hard to find that common number to make these the same. It's just really hard. It might be a huge power you end up with. And we only know our powers through a limited number. You know, like what, 2 to the 12, 4 to the 6. Sometimes it's hard. I think it's probably safer to just bring them down to a common base, like base 2, and think that way. But to do that, you've got to be able to know that that 3 down there is the same thing as a 3 underneath that, or a 3 on the bottom here. Lula and I were talking right when we came in here before a lot of you got in here. She was talking about how she likes logarithms. And some people hate logarithms. And I will say this, if you hated them as a 10th grader, most people like them a lot better as 11th grader, because I'm not teaching you anything new. And you're filling in more of the holes you might have had. So you're going to be better off. But I was saying how, to me, it's like a language that you don't know, but there's just not many letters in the alphabet or many words. But it's still learning a new language. But once you learn that small group of words, it's like, oh, I've got it. There's nothing else out there. It's just a matter of learning those. And I like to think that I give you enough practice problems to do that. But I would just, as you're going through the work, if you miss something, circle it in red. Make sure you go back over it again. Make sure you're checking and correcting, and you'll be filling in the holes of your logarithm cheese or whatever. And the fewer holes you have, the better off you're going to be. So with that in mind, oh, one other rule. Do y'all know this rule? If I were to give you something like that, what happens? That cancels. Now the key is, there has to be a 1 up front. So if I give you something like 2 to the 3 log base 2 of 5, can I cancel the 2 and the log 2? Not yet. What would I have to do to be able to do that? Swing the 3 up. And now that I have 2 log 2, now I can cancel. And I have 5 cubed, which you guys know is 1.5. But can it be uglier than that? Of course. What if I had this? Now the bases don't match. But could you make a match? How? Change that to a what? Let me just write this out. Change it to a log base 2 squared of 7. Now, can I cancel them now? No, that 2's still there, right? What can I do with that 2 though? Change it to a 1/2 up here based on what we had earlier. So a 2 down there becomes a 1/2. Now they match. 7 to the 1/2, which is square root of 7. Make it a little uglier. What if there was a 5 out front? What could I do? That 5 could become what? A 7 to the 5th, right? And then the 4 becomes a 2 squared. You follow me? The 5 swings up, so it's no longer there. But I still got to make that 4, so I change it to 2 squared. And before I cancel, what happens? I'd have to move the what? The 2 would come up and become a 2 in the bottom, 5 halves. Y'all seen this? and then these cancel and leave me 7 to the 5 halves, which is the same thing as the square root of 7 to the 5th. And if I did give you that, you could leave it like that. I'm not gonna make you multiply that out. But I probably wouldn't. I'd probably end up with numbers that you could multiply out. Y'all seeing this? Or I put a variable in there like x to the 5th, so you wouldn't have to multiply that. You seeing it? So I'm gonna throw a bunch of these things at you. And I think you'll be in good shape, hopefully. So let's check it out. What time do I have? 50. Oh, good.
Are we doing another test?
Not now. Dang it. No, you're right. I wish you'd have said something earlier, and I would have. I may have to just wait because I don't know if I'm gonna have time. If you're dying to see me, you can come out to school. But yeah, I don't know if I can get all this in. So maybe we can. Let's just see. So help me out. Log base 16 of 8. Do not say 1/2. Okay, I see that all the time. That's not a log rule. That's a algebra 2.7 or something. What is this? So that could be a 2 to the 4th. The 8 can be a 2 cubed. And you see how you're forcing it into a rule? Now that my bases match, what do I end up with? 3/4. What if it's this? Log base root 2 of 4.
4 is like root 2 to 4.
Okay, you could do that. Okay, I'm going to do it 2 ways. This way I would not encourage, unless you're really on your game. He's saying that 4 is root 2 to the 4th, which is true. And if you do it this way, you get what? 4 over 1, which is 4. That's great thinking. To me, that's much harder, but I don't know if your brain goes with it. I would look at it as that's a 2 to the half, that's a 2 squared, and 2 divided by a half is multiplied by the reciprocal. But if you can think that way, I think it's probably a little more risky if the numbers get uglier. But hey, it would have been fine with me. Very clever. What if I gave you something like this? Do you see where the bases would match? You got a 3 in both, right? There's your 3 cubed. But this is a 3 in the denominator. That doesn't fit my rules. It has to be in the numerator. But what could you do? That's 3 to the what? If it's in the denominator.
Negative.
-1? And you forced it into one of the rules? -1/3. What about this? Log base -4 of 1. Now I said anytime you log a 1 you get a 0, but I said as long as your numbers were okay. Am I allowed to have a negative down here?
No.
So if I have a 0 or a negative anywhere in a problem, what is it? D&E. Now, if it was log of base of +4 of 1, then of course it's equal to 0. Log of 1 is equal to 0. And don't confuse that with this. People all the time will go, oh, log of 1 is equal to 0, log of 0 is equal to 1. No. No, you can't log anything but a positive number, right? All right? All right, what about this? What if I gave you log base -2 to the 4th of -2 to the 10th? Can I log that? Now, really sloppy math teamers would go, no, it's a negative number. It is now, but by the time you get to doing the logarithm, is it negative? No, because this 10 gives me 10 negatives. That's going to change that to a plus. That 4 is going to change it to a plus. So you end up getting log of 10/4. Sorry. You end up getting 10/4, which is 5/2. But be careful. What happens if they're negative and one of these is odd? Then what? Then it's D and E, because that's going to remain a negative number. You can't log a negative number. Y'all seeing this? Okay. Couple other things. I think this is going to make perfectly good sense, but I may have talked about this last year. But doesn't it make sense that x has to be 5? If everything else in the problem is the same, and there's one difference, then the two differences must be equal, right? Now, jumping to this is skipping the whole, hey, I really need to log base 3 both sides, and that cancels that and brought to the x and cancels that. No, I don't need you to do that, but technically you do. But this property that says, hey, if everything's the same except these two things, then those two things would have to be the same. That's called the one-to-one property. One-to-one property. And it works with all kinds of stuff. Log of x minus 2 equals log of 7. Base whatever. How about base 6? Well, if everything but the stuff you're logging is the same, then what must else be the same? That stuff. Now I totally skipped the exponentiation part, didn't I? I didn't exponentiate both sides, cancel that out. That's the math. But the one-to-one property says, hey, if everything's the same except these two parts, everything, then these two parts must be equal. And then don't forget with logs, you always check your answers, because if you get something that when you plug it back in, you'd be logging a negative or a 0 or something like that, you have to throw it out. All right? Okay, so be careful on that because this happens sometimes. Let's see if I can make this work. No. I get people all the time that go, oh, the left side and the right side are exactly the same. So I can just cancel out the logs and do this. And I go, what do you mean the left and the right? This is not right. What do you mean the left and the right are the same? That is 2 logs. This is 1 log. Those are not exactly the same, are they? But wait, can you add 2 logs together? Now think about this. This would be x plus x minus 2 equals that. That's not right. But how do you add 2 logs together? So you keep the log that they have in common. Of course, you have to have 1s in front or swing that number up. And then you'd multiply that. Okay? Now what do you have? One-to-one property. Now you can still exponentiate, right? 2, 2, cancel, cancel. But instead of getting x plus x minus 2 equals 8, you get what? X times x minus 2. So don't come in here and just cancel logs like that. That's real sloppy. It's not math. It's, algebra 2.7. We don't want to do that. And then surely at this point, I have engineered the problem to be able to factor nicely, which would be my goal. And my answers end up being 4 and negative 2, right?
No, you got to check.
No, you got to check. And when I plug the negative 2 back in here, if it's false for anything, toss it. But when I plug the 4 in there, oh, I can log a 4, and I can log a 2, and it actually ends up working. I'm good. Not too bad. 3 minutes. There's a couple of graphing log problems in there, but it's about shifts and reflections and stuff like that. You think we're okay on that? We've already done this. I'm going to give you a basic one. Log base 2 of x plus 1 minus 3. What will we do to graph this guy? Left 1, down 3, and then that's gone. All I got to do is think about this. So what are the easiest 2 values to plug in here? Logging a 2 is great, because if I plug a 2 in there, I get log base 2 of 2, which is 1. So mark the point from here, over 2, up 1, and then always what's great? 4 is also great, but what's really, really great? 1. If I plug a 1 in there, I get a 0. But you are right, a 4 would give me a 2. And if you had room, an 8 would give me a 3. 2, 3. And then that right there would be my log curve, except what does it do? Dives down because they all have vertical asymptotes, right? And don't confuse a horizontal line with a horizontal asymptote. Does that have a horizontal asymptote? No. I got 1 minute. Is it worth looking at it, or do you want to look at it Monday? Monday? All right. Good times. Y'all have a great day.